In this example, we're asked to determine whether a given collection of vectors is linearly independent. The way to do that is to first set up a matrix whose columns are the given vectors. Then we should row reduce this matrix to determine the number of pivots. If we end up with a pivot in every column, going down the diagonal here, then the corresponding homogeneous system has only the trivial solution. If you imagine that I end up with a pivot here, and then a row of zeros here, then I would have x3 equals 0. And I substitute that into the equation above, and I'll end up with x2 equals 0, and so on. So we should row reduce this matrix whose columns are the given vectors. Okay, so I'll do that next. So the first thing I'd want to do is get a 1 in that top left corner. And so always take the simplest row operation that you can. So if we do a swap with row 1 and row 2, then we end up with the 1, 0, 2 on top, 3, 4, 2 here, the 2. Okay, now we want to get zeros below that leading 1 in the first row. So I'm going to do 2 row operations in sort of one step here. First, I want to get a 0 in this position. So to do that, I would use the row operation -3 times row 1 and add that to row 2. So we're going to leave row 1 the way it is. -3 row 1 plus row 2. So -3 plus 3 is 0. -3 times 0, so 0 plus 4, so we still have a 4 in this entry. And then -3 times 2, so -6 plus 2, so -4. Okay, let me, before I write a new matrix, go ahead and do a row operation that gets a 0 in this entry. So to do that, I would use the row operation 2 times row 1 plus row 3. And so that'll give me 2 plus -2 is 0. 0 plus 1 is 1. And 2 times 2, so 4 plus -5 is -1. Again, always use the simplest row operation you can. So if I want to get a 1 in this entry here, I would just do a swap. Oh, or actually, we could do 1/4 times row 2. That would also be pretty straightforward in this case, since these are both multiples of 4. So I'll do that. 1/4 times row 2. Either of those row operations that I mentioned would work, though. There's a lot of times there's more than one row operation that works nicely. Alright, so if I multiply everything in row 2 by 1/4, I end up with 0, 1, -1, which is exactly the same as row 3 there. And when you see that, in the following step, you can always make one of those duplicate rows disappear. In this case, I'll go with my usual order here. So I'm going to get a 0 in this entry here with the row operation -row 2 plus row 3. And that's actually going to eliminate all of row 3. But I'll write that out here. So row 1 will stay the way it is. Row 2 will stay the way it is. Forgive me for writing in the bottom here. And then we have 0 plus 0, so that's 0. -1 plus 1, so that's 0. +1 plus -1, so that's 0. So we've arrived at the reduced or the row echelon form of this matrix. Since we do have free variables, so there is a column that does not contain a pivot, there is a free variable. If we're going to write out the solution set, x3 would be a free variable. And that guarantees that the corresponding homogeneous system has a non-trivial solution, which means that this collection of vectors is linearly dependent. So I wanted to talk through the logic there, but overall, what we've discovered is since there is a column that does not contain a pivot, then this collection of vectors is linearly dependent. If we had found a pivot in row 3, then this collection of vectors would be linearly independent. But like I said, we've got x3 is free in this case, and so the collection of vectors is linearly dependent.